Hello and welcome back to the machine learning video series. With the last video, we have completed our basics on the linear regression model. Now let's look at the next most used regression, which is logistic regression. We have discussed problems that dealt with continuous label values. However, many problems that we come across require classes or categories as outputs. For example, if we want to detect an animal in a picture, we would expect the name of an animal in our output from a neural network, not a numerical value. But there is a major problem with such categorical output because the loss cannot be calculated in the same way as regression. That is, the predicted and actual output cannot be subtracted from each other for obvious reasons. So, to denote categorical values, we use integers. For example, we can assign 1 to dogs and 0 for cats. If our output is 1, a dog is predicted, and if the output is 0, a cat is predicted. Other integers can also be assigned in case of more number of classes. For once, consider a mathematical function called sigmoid. From the graph, it is evident that in the sigmoid function, if the input value is greater than 0, its value comes out to be close to 1. For values less than 0, its value comes out to be closer to 0. The value of sigmoid is exactly 0.5 at input 0. As discussed, we will denote one class by 0 and the other by 1. Now we can use our earlier hypothesis to calculate wx plus p. If we feed this to the sigmoid function, we will get output between 0 or 1 that can be rounded off to one of the values. Hence, we got categorical output that depends on the previous equation, wx plus p. Problem solved. We can now use gradient descent to optimize our model. Now we need an error function that we can minimize to generate more accurate predictions. We have also seen that MSE cannot be used in this case because we cannot subtract categorical values. Instead, we come up with a new equation for the cost function. This time, the cost function is defined as j equal to minus bracket open y multiplied by log of p plus 1 minus y multiplied by log of 1 minus p, where y is the actual class and p is the predicted class. It looks complicated but makes perfect sense. We know that log of 0 is infinity and log of 1 is 0. So, if the predicted and actual class are both equal to 1, the equation becomes 1 into 0 plus 0 into infinite, which is 0. Same goes for when both predicted and actual class are 0. However, when actual class is 1 and predicted class is 0, the equation becomes j equal to minus of bracket open 1 into infinite plus 0 bracket close, which is infinite. Same for when actual class is 0 and predicted is 1. We see here that for correct prediction, the cost is 0, but for incorrect predictions, the cost is very large. Hence, this is a very useful cost function. The rest of the process is same. We differentiate the cost function and find out the appropriate values of dependent variables. That is, we apply gradient descent to the model with our new cost function. We can deal with classes that are represented by 0 and 1 using sigmoid function. But what if we need to classify into more than 2 classes? Most real-life applications will actually require more than 2 classes. For example, if we want to classify images of handwritten numbers, we have 10 possible classes corresponding to numbers 0 to 9. We do not have a function that can give us any number of classes as categorical output. In this case, we use the one versus all approach. This means that we take one class at a time and treat all others as another class. Then we run the classifier and save the output class predicted by the model. This was a glimpse of logistic regression. Next video will discuss on different approach to machine learning problems than regression. See you in the next video. Thank you.